We'll be taking a look at lesson 2.4 in this video. And we should be good here. There we go. So we're working our way through Unit 4, Chapter 2 in our textbook, which focuses on the properties of angles. And this lesson, 2.4, focused on the angle properties in polygons. As with each previous lesson, we learned about the various properties, whether it was with parallel lines or with triangles, and now with polygons. So we're going to gather together what that information is, and then we're going to use those to solve various problems. Keep an eye out for a couple of words that are going to pop up. That's convex and concave. And in fact, we're going to start with that. What is the difference between a convex and a concave polygon? And of course, first of all, let's make sure that you understand a polygon simply means a figure that has many sides. So a convex and concave polygon, well, here are two examples. And I think what jumps out at you is in the concave one, you have this indent in the side. Now, a definition of this, to keep it clear, would be that a convex polygon is a polygon in which each interior angle measures less than 180. So it never gets wider or bigger than a straight line. In fact, it never gets to be a straight line. A straight line would make the polygon basically just a straight line. But if you look at this one, you're going to see that you've got this angle that is a reflex angle. And that's what creates the indent effect on the side, like a squished in soda can or pop can. So convex and concave, or non-convex as they've also called it here. Okay, so the first question we're going to try to tackle is, how is the number of sides of a convex polygon related to the sum of its interior angles? Now we're going to use a fairly simple pattern to help us with this. We're going to use our shapes. This one is a quadrilateral, and we're going to create triangles inside that go from one corner to the next. And so just if I were to draw a line right down through that, I'd have two triangles. And that would mean that the sum of this guy's interior angles are the same as two triangles. And so the pattern that we're starting to see looks a little bit like this. The number of triangles inside a triangle, is 1, which is 180. The number of triangles inside a quadrilateral are 2, which is 2 times 180. Then we played with these in class, and we drew a pentagon, and we drew a hexagon, and we realized that this pattern was emerging, that the number of triangles was always 2 smaller than the number of sides. And that allowed us to find the sum of our angle measures pretty easily. Now, putting that all together, we can actually come up with a formula that will do this work for us. The sum of the interior angles of a polygon are equal to 180 times n being the number of sides of the polygon, minus 2. Now, before we do our first question, I just wanted to make sure that you remembered what a regular polygon is. A regular polygon has equal sides and equal angles throughout. It's completely uniform. So determine the measure of each interior angle of a regular 17-sided polygon. Now, before we can find out what each one actually is, we need to know what the sum is. And so I'll take the sum being 180 times n minus 2, 17 minus 2 being 15, and these two multiplied together gives me 2,700. That's the total of all of the angles. So if I take that total and divide it by the number of sides being 17, I will find that I have angles just around 159 degrees. Now, you could also turn that into a formula all of its own. And you could say, if I need to find one interior angle, I could take the sum and divide it by the number of sides. Really, that's a fairly straightforward jump that we're making. And so in many ways, it's not really worth it to memorize a new thing. But it's there in case you'd like to have those things handy. Okay, now here's something that's kind of interesting and in some ways almost hard to picture. And that is that the sum of the measure of exterior angles of any convex polygon is always 360. Now we know that the sum of the interior angles changes all the time. The more sides we have, the larger the number seems to get. But for the exterior angle, it stays the same, which is a curious, unexpected thing in many ways. Now for this one, In order to be able to prove this deductively, to be able to show you, it's a little bit of a tricky proof. And so, as a result, what we're going to do instead is keep it to pentagons for this one. And I think that will help you realize how it would work for everyone. But show that the sum of the exterior angles of a pentagon is 360. So, we're going to prove this deductively for the shape of a pentagon. All right, so I had to do a little bit of patch up work to my shape that I had drawn in my notes, and I realized that I had kind of messed up my angle numbers. So bear with me; it's not quite as fluid as I'd like it to be. But what I've done is I've labeled all of the interior angles, and I've labeled all of the exterior angles. Now, what I notice about them is that the interior and the exterior together form a straight line. So I know that they are supplementary and add up to 180. So 1 plus 2 is 180, 3 plus 4, 5 plus 6, 7 plus 8, and 9 plus 10. They all add up to 180. Now, if I were to take all this and add it all together, now what I know is that all of those odd numbered angles are all the sum of the interior angles. And I happen to know how to find that. And so I know that it's actually 540 degrees. So I'm just going to put 540 to keep it simple. And then I still have all of my exterior angles still added up together. And then if I take this would be 180 times 5, I get 900. If I move that 540 over to the other side, I realize that I do get 360. So all of the exterior angles of a regular convex pentagon equal 360 degrees. Okay, so here's kind of your last type of question that we might give you, kind of the most difficult in some ways. What type of regular polygon has an interior angle 3 times the exterior angle? Now, in something like this, you might be able to just think it through and come up with some examples by guessing and then checking your work. But we want you to be able to do this algebraically, so please take note of the process that you would use to do that. So I drew a little diagram. Here's my funny shaped polygon. And I'm just looking at one of the corners and I'm extending it so that there's an exterior angle, interior and exterior. And what I've said is I'm going to call the exterior angle x and the interior 3x, because if you remember from the text of the question, the interior angle is 3 times the size of the exterior. And what I know is that those two add up to 180. So simply doing the algebra for it, it turns out that x, the exterior angle, is 45. Now, if you wanted to know how many sides this polygon has, perhaps the easiest way might be to simply take, I know that all the exterior angles add up to 360. I know that one of them is 45. And so that seems to mean that I have 8 sides. An octagon has interior angles that are 3 times the exterior angles. Okay, there you have the main core of our lesson and some of the exercises that you might expect to see. Here are some, your homework. So this is from the textbook. Quite a number of questions in here. Some of them are proofs. So be on the lookout for those. Then you have a worksheet. This one is actually optional. It's, again, filling in some guided proofs. And this one is one that you need to do as well, 2.4 worksheet number 1. All right, so remember, please do your work carefully and then come with any questions that you have. Don't forget to do your homework. Okay, thanks everyone.